Hello, my name is Ian Sierra and this is the Lab 3 video report. The purpose of this lab is to determine the distance dependence of the magnetic field due to a small bar magnet and look at the differences between this and distances determined by equations for the magnetic field on and off axis using our experiment and a computational model. This experiment uses the concepts of magnetic fields and magnetic dipoles. The formulas that are used in this lab are the distance dependence formula and formulas for a magnetic field of a dipole, including the general formula, on-axis formula, and perpendicular formula, which all solve for the magnetic field. Now on to the procedures. I used the app Teslameter to find the magnetic field values. I compensated for magnetic north by aligning my phone so that the x-coordinate of the magnetic field would be 0. The net magnetic field for my location was 48.7 and the net magnetic field found on the app was about 47.5 to 48.5 microteslas, which was appropriate for this experiment. The magnetometer was found on my phone by setting it perpendicular and parallel on the meter stick and finding the appropriate absolute x and y components for each direction. Then the distances were recorded in meters where the x components of the magnetic field were equal to the selected values on the screen. This was repeated 3 times to calculate the averages of the distances. This information was put into an Excel sheet to help determine a value for n. For measuring the off-axis magnetic field, I had to find a perpendicular distance where the net magnetic field was equal to about 100 microteslas and record the y component of the magnetic field. Then I moved up that same distance and recorded the components of the magnetic field, where the phone is the distance d from the magnet. This procedure is repeated 2 more times. The value for By is corrected by taking the By measured and subtracting it by By Earth. These recorded values are entered into the spreadsheet to find the magnitude of the net magnetic field, which we will use to compare to the values calculated by the code. Some observations that I discovered while completing this experiment were when the magnetometer is far away from the magnet, it measures a near zero magnetic field in the x direction, and as the magnetometer moves closer to the magnet, the measured x component of the magnetic field increases. Now to the calculations. We first want to determine the value of n from the slope equation on the Excel sheet, which can be translated to ln of bx equals to ln of k plus n times ln of r. This comes from the average distances we took at the select x components of the magnetic field, which creates a graph with the slope equation. N is found to be negative 2.5506. We then evaluate the value of k by setting r equal to 1 so that we are only left with ln of bx and ln of k. Using the fact that the ln of bx is equal to negative 13.958, we can take e to the negative 13.958 to find the value of k. Now we use the equation of B, dipole on axis, and set it equal to the distance dependence formula to solve for the magnitude of the magnetic moment mu, which comes out to be 4.336. Now to the code. The calculated value of the magnitude of the magnetic moment is entered. A function is then created to find the magnetic field with inputs of mu and r and using the formula for finding the magnetic field of a dipole. Observation locations are entered using the distance defined above with 2 locations on the axis and 4 locations perpendicular to the axis. The magnetic field function is used to calculate the magnetic field and arrows are made for a visual representation. This is done for all of the defined observation locations on the axis and perpendicular to the axis. Then we visualize the magnetic field off axis using the value for the average d we found from the experiment to calculate d. The magnetic field off axis is calculated and an arrow is created to visualize the magnetic field. When we run the code, we see a white cylinder representing the magnet, the orange arrows representing the magnetic fields on axis, the cyan arrows representing the magnetic fields perpendicular to the axis, and the magenta arrow representing the magnetic field 45 degrees from the axis. The values are printed for all of the magnetic fields and the value of D. When we compare the off-axis values of the magnetic field, the main difference is that the y component is negative on the experimental value, while it is positive on the model value. These differences could be due to the positioning of the magnet and the unintentional incorporation of the Earth's magnetic field in the experiment. On to the conclusion. If I had laid out the meter stick at some intermediate angle with respect to Earth's magnetic field, the results would be drastically different because it does not only include the magnet's magnetic field, but also the Earth's magnetic field is included in the results. If I had used the two identical magnets stuck together end to end, the magnetic field would be stronger. Thus, the magnitude of the magnetic field would about double in value. Thank you for watching.